Hello and welcome to today's lesson. Today we will consider the topic equilibrium. And in physics, there are different types of equilibrium. There is thermal equilibrium, there is chemical equilibrium, there is also mechanical equilibrium. And for each of these types of equilibrium, there are conditions that must be satisfied. For example, in the case of thermal equilibrium, for two bodies to be in a state of thermal equilibrium, there should be no net flow of thermal energy between both bodies. And in that case, the body will be at the same temperature. Today we consider mechanical equilibrium. For mechanical equilibrium, there are two conditions that must be satisfied. The first condition is that the vector sum of all external forces acting on the body must be zero. The vector sum of all external forces acting on the body must be zero. And this can be written mathematically. We have here the vector sum of all forces, which we call the net force, is equal to, from Newton's second law, the net force is the time rate of change of the linear momentum. And the first condition says that this net force has to be equal to zero. There are implications. The first is that for a body that the net force applied to it is zero, the linear momentum of the center of mass of the body will be constant. And for a body of constant mass, the body will either remain at rest or it will move with a constant velocity. Okay. Now, a body that satisfies this first condition, that is a body where the net force applied on it is equal to zero, is said to be in a state of translational equilibrium. The state of translational equilibrium. This is the first condition. The second condition for mechanical equilibrium states that the vector sum of all external torques about any point acting on the body must be equal to zero. As we go on, we are going to explain what we mean by torque, and we also introduce how to calculate torques. But for now, it's sufficient to state that the torque is the turning effect of a force. And this second condition can be written mathematically. We have here the vector sum of all external torques about any point is equal to the net torque. And this net torque is equal to the time rate of change of the angular momentum. This particular expression is the rotational analog of Newton's second law. In Newton's second law, we have that the net external force is the time rate of change of the linear momentum. But when we look at the angular or the rotational analog, we have that the torque, the net torque, which is the turning effect of the force, is equal to the time rate of change of the angular momentum. And the second condition says that this net torque has to be equal to zero. The net torque has to be equal to zero. And by implication, when the net torque is equal to zero, the angular momentum of the body about any point will be constant. And for a body of constant mass, that will imply that the body will either be at rest or it will rotate with a constant angular velocity. Okay. This second condition, the body that satisfies this second condition is said to be in a state of rotational equilibrium. Okay, so the first condition is called translational equilibrium, and the second is called rotational equilibrium. And when a body satisfies both conditions, that body is said to be in a state of mechanical equilibrium. Now, in the statement of these conditions and in the implication, we saw that either the body will remain at rest or it will be moving. And when it is moving, it has to move with a uniform motion, either a uniform linear momentum or uniform angular momentum. The common misconception is for students to assume that all bodies in equilibrium has to be at rest. No, that is wrong. There is the case where the body is at rest, and we call that static equilibrium. When the body is at rest, we call that static equilibrium. But the body can be in a state of uniform motion, either motion in a straight line, or if it is rotating, it will rotate with a constant angular momentum. And in that case, when the body is in motion, we say that the body is in a state of dynamic equilibrium. Okay? So this concept that we have introduced will be important to us. We use it to solve some simple problems. The First problem we consider, the first type of problem will be problems where we apply just the case of translational equilibrium. Then we have also solved some problems where we use rotational equilibrium. And then we are now going to move towards problem where we use the both conditions and we apply the full statement of mechanical equilibrium. Okay. The first sample problem states that an object of mass 10 kg is supported by two strings, which makes angles of 52 degrees and 38 degrees with the vertical. Calculate the tension in both strings. We have to use G, that is the acceleration due to gravity, equal to 9.8 meters per second squared. Okay. Now, the solution of this problem will follow the same procedure as the same procedure we used in previous examples. And the procedure is to first draw a diagram that illustrates the problem. So let's do that. The diagram here, we have an object of mass 10 kg supported by two strings. So the strings, they have to be tied to support. So we have one string and we have the other string. The angle between the string and the vertical, the first is 52 degrees and the second makes an angle of 38 degrees. Now, the angle, if I draw a vertical over here, this angle will also be 52 degrees, okay, because we have here alternate angles. And this angle here will be 38 degrees. So next thing we have to do is to identify all the forces acting in this system. And the first force we can identify is the weight of this object. So the weight is given by the mass multiplied by the acceleration due to gravity. We can write the result at once because we know the mass and we know the acceleration due to gravity. The mass is 10 kg times acceleration due to gravity is 9.8 meters per second. And that gives us a weight of 98 Newton. Okay? And over here, there will be a tension in this string. I will label that T1. And in the other string, we are going to label T2. Now, it is the force from this string that supports this mass. And this statement, the 10 kg mass supported by the string, implies that the mass is at rest. Because without the string providing the support, the mass will be in free fall due to its weight. So the fact that the string supports this mass implies that the mass is at rest. Therefore, the next step where we draw the free body diagram, the sum of the forces acting in this system should sum to 0 because the system is at rest. Therefore, it is in a state of equilibrium. And the first condition is that the net, that is the vector sum of all forces, should be 0. So in the free body diagram, I will represent my forces. The first is the weight acting downward, and that has magnitude of 98 Newton. And over here, 38 degrees to the vertical, I have my, so this 38 degrees, we have the vector T2. And on the other end, at 52 degrees, so this will be 52 degrees, I have my angle T1. Okay, so we have that this system is in equilibrium, meaning all forces should sum to 0. And if all forces sum to 0, the vector sum of the x component of all forces should be equal to 0. Likewise, the vector sum of the y component of all forces should also be equal to 0. Okay, so let's look at the forces and calculate their components. For the x component, C1, we have an x component that points to the left. That is the negative x direction. Let's state our sign convention. It is the minus x direction. It is plus x. Over here we have plus y, and below we have minus y. So the x component of t1 points to the negative x direction. So if we have to write that out, it will be the sign will be minus. How about the magnitude? We can make use of the trigonometrical ratio. We have that the sine of an angle theta is equal to opposite over the hypotenuse. And we also have that the cosine of an angle is equal to the adjacent over the hypotenuse. So this, my perpendicular here to the x and the y axis, I have two right angle triangles. And the x component of my force T1 is the length from the origin to this point, which will also be equal to the length from the y-axis to this point, because this forms a rectangle. And this side, which I need, the x component, is opposite to 52. So in this ratio, if I make opposite the subject, the opposite is hypotenuse times sine theta. So we have gone over this in the previous class. This is just a brief reminder. So the opposite is hypotenuse here. Hypotenuse is T1, the magnitude of T1, sine, and the angle in question is 52 degrees. Then we look at the next vector, which is C2, the force T2. The x component of the force will be a vector from the origin to this point, and it points to the positive x direction. So we have here plus. And using the same ratio, the side we need is the opposite of 32. And opposite is hypotenuse, which is T2 sine. And in this case, the angle is 38 degrees. And this has to be, as we have here, let's write it again. It's equal to 0. Okay? Let's do that of the y component. We have three forces. Let's begin with T1. The y component of T1 is, again, the side we need, which is the y component, is adjacent to the angle 52. So we use the second ratio, cosine theta equal to adjacent over hypotenuse. Therefore, adjacent is hypotenuse. In this case, hypotenuse is T1. Cosine, the angle, and the angle is 52 degrees. The sign is plus positive because the y component of T1 will point upward, which is the positive y direction. Same with the y component of T2, it also points the positive y direction with magnitude T2 cosine 38. We also have the weight which acts downward. So the weight already points in the y direction. Therefore, it will have no, okay, I did not mention, the weight has no x component. That is why we had no plus 0 here. There should be a plus 0 because the x component of the weight is 0, but there's no need to add that. And the y component is the entirety of the magnitude at 8 degrees. So the key here is, as we mentioned in the earlier classes, a vector has no components in the perpendicular direction. So 98 Newton, which is the weight, is in the y direction. Therefore, it will have no x component. And this y component points to the negative y direction. The vector itself points to the negative y direction. So the magnitude here is the sign is negative, and the magnitude is 98 Newton. And that has to be equal to 0 because this body is in equilibrium. Okay? So we have two equations that we have to solve. This is equation 1, and this is equation 2. We solve this system of linear equation, we solve it simultaneously, and we can use the substitution method. So what we do is, we take equation 1, let's start from equation 1, we make T1 the subject, and we can take the entirety of this term, everything here, we take it to the other side of the equal sign. That will give us the equation T2 sine 38 equal to T1 sine 52. And to make T1 the subject, we divide both sides by sine 52. And we're going to have that T1 is equal to T2 sine 38 divided by sine 52. Okay, this is my equation 3. So we continue, and we continue by substituting T1 into the second equation, equation 2. So I will substitute T1 into equation 2. And if I do so, in place of T1, I will have T2 sine 38 divided by sine 52, and everything will be multiplied by cosine 52 plus T2 cosine 38 minus 98 equal to 0. Okay? We have T2 in these two terms, so we can open a bracket. We can put them in brackets. So we have T2, and then in bracket, the first term, what remains is sine 38 times cosine 52 divided by sine 52 plus, and over here, what remains after I remove sine? I remove T2 will be cosine 38, and that has to be equal to, I'll take the entirety of minus 98 to the other side of the equal sign, and it becomes plus 98. So T2 now stands alone, and I can make it the subject. I have to divide both sides by what is in this bracket. Now I have left that T2 is equal to, we have 98 divided by sine 38 times cosine 52 divided by sine 52 plus cosine 38. You can calculate this with a calculator, and if we do so, you have a result of T2 equal to 77.2 Newton. Okay, so this is T2. So since we have calculated T2, we can substitute T2 into equation 3. And equation 3 here says T1 equal to T2 sine 38 over sine 52. So once you know T2, you can immediately calculate T1 using equation 3. So we have substituting T2 in equation 3, and we have T1 okay, T1 is equal to T2, but we calculated T2 to be 77. Okay, let's write it again so there will be no confusion. Let's write it. T2, so I'm writing equation 3. So T2 is T1 equal to T2 sine 38 divided by sine 52. Okay, so after substituting, if I substitute, T2 will be 77.2, and that will be 77.2 times sine of 38 divided by sine of 52. Okay, and that gives me, when I calculate this, 77.2 times sine 38 divided by sine 52 is 60.3 Newton. Okay, so we have calculated our, we have solved the question. The question says calculate the tension in both strings. So the direction of the tension point along the strings, and the magnitude is T1 equal to 60.3 Newton, and T2 equal to 77.2 Newton. Okay, so these are the results and final answer. Okay, so I withdrew the free body diagram to make a point that we can use different methods, because all we did here was to sum the vectors and equate the sum to 0 according to the first condition, because we know the body is arrested for, it is in translational equilibrium. At this point, we can use any suitable method for summing vectors, any suitable method of vector addition. And one method that we can use is the fact that when we have vectors to sum, let's sum three vectors. Let's call this vector A, let's call this B, and let this be C. Okay, say we want to sum these three vectors. One way of summing them is to join them head to tail. So this is often called the diagrammatic method because we draw the vector to scale and we join them head to tail in order. So I start with vector A, but the order doesn't matter. It can be A, B, C, B, C, A, or C, A, B. You have the same result, but maintain the same magnitude and direction. So I've translated A, the vector itself doesn't change. Likewise B, I'll translate it so that I'll have the tail of B joins to the head of A. So this is B, and then the final vector C. So the sum of these three vectors A, B, C is the vector from the starting point, we shall call 1, to end point, we shall call 2. So a vector from 1 to 2, I'll call this R, the resultant vector. So R is equal to A plus B plus C. So this is one way of summing vectors. Okay, now the order doesn't matter. I can as well start with C. So let's start with C. So this is C, and to C I'll add B. This is B, and then A. And the sum of these vectors will be the vector from the starting point to the end point R. Okay, so the key point here is that you can think of this as a displacement. If someone displaces from the starting point 1, person moves to this position here, and next traveling along B moves to this position, and then move finally along C, which is 2. The final displacement, which is the sum of this displacement A, displacement B, and displacement C, is simply the displacement from the starting point to the end point. So this is one way of thinking about it. So we're going to use this method to solve our problem, and we should get the same result. Okay, so we start with vector, the weight which points downward, with magnitude 98, and to that we join C2. You can join C1 or C2 first, doesn't matter, just maintain the same magnitude and direction. So here is C2. Now this vector sums to 0. That implies, as in the case of displacement, if the net displacement is 0, it implies after summing all the displacement, the object or the person returns back to the starting point, meaning the vectors form a closed path. So since these three forces sum to 0, C1 should take us back to our starting point. We have here C1, and we have a triangle. And this triangle, the angle here, that is angle between T2 and the vertical, is 38 degrees. Okay, and here the angle between T1 and the vertical is 52 degrees. What is angle here? You can use the formula. Since the sum of angle in a triangle is 180. Okay, so it's 180 minus 52 plus 38. And 52 plus 38 is equal to 90. So the angle is 180 minus 90. And that is equal to 90. So this angle here is actually a right angle, and we have here 90 degrees. So you see that we have reduced the problem of finding the vectors T1 and T2, the forces T1 and T2, to the problem of solving or finding the unknown sides in a triangle, so a problem of geometry. And we have many formulas for calculating, and we have many formulas in geometry. And one formula that we can use here, because what we need is to find two unknown sides in a triangle where we know all the angles. And a stable formula we can use is the sine rule. And what does the sine rule say? Sine rule says that the ratio of the sine of an angle to the opposite side is the same for all angles in the triangle. Okay? So let's apply that here. Let's start with T1. We have sine. It can be the ratio can be of in any order. But let's have T1 divided by the sine of the opposite angle, which is 38. So T1 divided by sine 38 should be equal to T2 divided by, so the angle opposite T2 is 52. So T1 is opposite this angle 38 and T2 is opposite the angle 52. Okay, and this should be a ratio of T2 to sine of 52. That should equal to the ratio. This side is 98 Newton to 98 divided by, and the angle opposite that is 90. So sine 90. And this is 98 over sine of 90 is 1. Let me write it here. Sine 90 is equal to 1. So this becomes 98 over 1, which is just 98. So this is actually two equations in one, and we can use them to solve for the unknown. So if I equate the first term to the third term, I can use that to solve for T1. So making T1 the subject, T1 is equal to 98 sine 38. It should be over 90, but sine 90 is 1 over sine 90, which is 1. So it is just 98 sine 38, which is equal to 60.3. And for T2, we equate these two. We use those two terms, second and third term, and that is T2 equal to 98 sine 52, and that will be equal to, that is equal to 77.2. These are forces, so they have unit of Newton. And this result, T1 90.3 and T2 77.2 is the same as our previous result. So when we come to summing vectors, we can use any suitable method and we end up with the same answer. Even in the first case where we have a system of linear equations, we also have multiple methods, different methods for solving a system of linear equations. And this equation here, if we solve to get T1 and T2, we can solve using any suitable method. Okay, so that's that for the first example. Our result is T1 equal to 60.3 Newton and T2 equals to 77.2 Newton. Let's move to the next example.